Hello and welcome in this OpenFOAM tutorial involving the simulation of a pool fire. The tutorial is aimed at people who have minimal experience with using OpenFOAM. The tutorial will demonstrate how to set up the geometry, briefly go through the case files, and running a simulation. For this purpose, OpenFOAM version 2206 and the FireFOAM solver will be used. It is worth noting that the structure of the tutorial, certain files and keywords can be specific to the OpenFOAM version and the solver used in this tutorial. Nevertheless, the basic principles are very similar regardless of the OpenFOAM version or the solver you plan to use. A typical OpenFOAM case will consist of three folders: 0, constant and system. Additional files like scripts can also be present for automating several processes when generating the mesh or for cleaning a case. We will examine some of these scripts later on. Let us first take a brief look at the different folders of a case. The 0 folder contains the initial and boundary conditions of the case. These conditions have to be defined for every variable that the solver uses and for every boundary of the computational domain. There are files related to chemical species, while any other species not explicitly defined in the 0 folder are assigned default conditions defined by the user. The initial and boundary conditions for temperature, velocity, radiation, subgrid scale thermal diffusivity, subgrid scale kinetic energy, subgrid scale kinematic viscosity, and pressure are also defined. For simplicity, we will only examine the most important boundary conditions of this tutorial. The mass flow rate in kilos per second is assigned for velocity at the burner based on the desired heat release rate and the heat of combustion of the fuel. The velocity at the floor is here set to 0. The ambient temperature and the temperature of the fuel at the burner are both set to 293 degrees Kelvin, while the floor is treated as adiabatic. The mass fraction of the fuel at the burner is set to 1, accounting for both the advective and diffusive mass fluxes. The initial concentration of air, on a mass basis, is set to 23.3% oxygen and 76.7% nitrogen. In the boundaries of the domain where air entrainment is expected, a combination of certain boundary conditions for pressure and velocity is required. The constant folder contains the submodels related to turbulence, combustion, and radiation, among others. The reactions, along with the considered chemical species, are defined in the reactions file. In this case, we consider a single-step, infinitely fast chemical reaction between fuel and oxidizer. The constant folder also contains the coefficients for determining the temperature-dependent thermophysical properties of the species. The thermophysical models and the gravitational acceleration, along with its direction, are also defined. Finally, we declare that the gas phase needs to be solved, which is true in our tutorial. The rest of the files are less important, while other files are related to pyrolysis, water spray, and surface film, which are not used in this tutorial. For this scenario, we will run a large eddy simulation using the one-equation turbulence model. For combustion, the eddy dissipation model will be used. The constant radiative fraction approach is employed for radiation, which considers an optically thin flame. In this case, a radiative fraction of 20% is considered for methane. The system folder contains the geometry and the mesh of the case. The time controls, like the total running time of the simulation and the time step, are also defined here. The temporal and spatial discretization schemes, the tolerances when solving the equations, and any under-relaxation factors are included here as well. The method of decomposition and the number of processes if a simulation is run in parallel can be defined. 2 more files are included, which are required for creating the burner in our scenario and will be discussed later on. The computational domain will be a rectangular box with a side length of 1 meter and the fire placed in the middle of the floor. We first define the vertices of our domain, which in this case will be 8. The numbering of the vertices starts from 0, hence the vertices will be labeled from 0 to 7. The starting point of our coordinate system is taken as the center of the floor to create the domain. We then define a block with these 8 vertices, starting with the plane defined by vertices 0, 1, 2, 3 and followed by the plane defined by vertices 4, 5, 6, 7. We then consider a uniform grid size with 50 cells in each direction, resulting in a 2 cm grid size. Finally, we have to define the 8 different boundaries of the computational domain. This includes their name, type, and the vertices which identify each one of them. When looking the box from the outside, we define the different boundaries by listing their vertices in a counterclockwise manner. That would mean 7623 for outlet, 0473 for the left side, and so on, by typing the command block mesh in the terminal, the computational domain, and the mesh will then be created. At this point, the burner boundary is not yet created but will be made in the following step of the setup. The command check mesh provides some information about the mesh and will identify any possible errors in the creation of the geometry. If everything is set up correctly, a mesh OK message will appear at the end of the report. The command toposet is used to select the faces of the computational domain that will be used for creating the burner. In the toposet dict file, 2 points are defined which create a small box in order to select the faces inside a 0.2 meter by 0.2 meter square on the center of the floor. We call this set of faces burner faces. The burner is then created through the create patch command based on what is defined in the create patch dict file. In this file, a new patch called burner is created from a set of faces called burner faces. In our tutorial, there are 3 scripts available: pre, clean, and run. The creation of the computational domain mesh and the burner is automated through the pre script. The script performs the 3 operations block mesh, toposet, and create patch automatically and in a sequential manner. The clean script will clean a case after it has been run, while the run script runs the simulation in parallel. To run a serial simulation using one processor, simply type the command firefoam in the terminal. To run a simulation in parallel using multiple processors, simply run the run script or type the appropriate command in the terminal. The simulation will start running and the output will be displayed on the terminal. The simulation will run for the time period specified in the control dict file, while results will be saved occasionally for visualization. This concludes today's tutorial. Thank you for watching the video.